Well, welcome to this online revision session to AQA M2, in which I will be considering the January 2010 question 4 on kinematics involving vectors. As you can see, you are given the velocity at time t of a particle in terms of I, j and k, where I, j and k are the base vectors, I being in the direction x, j being in the direction y and k being in the direction z. Part A, we are asked to find the position vector of the particle in general terms, given that when t is 0 it has a position negative 5i plus 6k. Well, to work out that first part, we need to remember that to get the position vector from the velocity vector, we will need to integrate. And so to integrate a vector, remember we have to integrate the separate components. So firstly we've got to integrate the I component, so the integral of 4t cubed will be t to the 4th. The integral of 12t is minus 6t squared, and the integral of 3 is 3t. And then we need to remember that since we're integrating, there is a constant of integration, so I'll call that constant c1. Similarly, if I integrate the 5j, that will just be 5t plus again a constant of integration, call that c2. And then finally the integral of 8t will be 4t squared, and again plus some constant of integration, which I'll call c3. Now, having got that, I then need to consider the fact that when t equals 0, r is equal to minus 5i plus 6k. Now for this particular value of t, the t to the 4th, the 6t squared, the 3t, the 5t and the 4t squared are all 0. And so c1 would have to be negative 5. c2, since there's no j's in the expression when t equals 0, that's 0. And c3 will have to be 6. And so r will become t to the 4 minus 6t squared plus 3t minus 5, lots of I, plus 5t j plus 4t squared plus 6, lots of k. 4 marks for that part of the question, for realising that you need to do an integration. That will give you a method mark. For obtaining an appropriate form for that integral, you'll get 1 mark for that answer, and specifically a mark for involving the constants of integration, and then finally an accuracy mark for your final answer to that part A. Moving on to part B, they ask you to find an expression for the acceleration, so you need to remember that for acceleration you need to differentiate that velocity vector with respect to time. So again we differentiate the separate components. So the differential of 4t cubed is 12t squared. The differential of minus 12t is minus 12. Differential of 3 is 0. So that gives you the components of I. Differential of 5j, well the differential of 5, since it's a constant, is 0. And then finally the differential of 8tk, well the differential of 8t will just become 8. So 2 marks, 1 mark for realising that you've got to differentiate it, and then 1 mark for the accuracy of your answer. Moving on to part C, it then says find the magnitude of the acceleration at time t. Do not simplify your answer. So to get the magnitude of a vector, you take the square root of the squares of the components. So to get that magnitude in part C, you will need to take the square root of those components of the acceleration. So back in part B, we found that the components of I are 12t squared minus 12, so that has to be squared, and then the component of k is 8, so that becomes 8 squared, and that has to be square rooted. And notice the question said do not simplify your answer, so that will do just fine. You don't have to square out the 12t squared minus 12 all squared or anything like that. So that's your answer straight through. So again, a method mark for realising that you're using Pythagoras on vectors, and then an answer mark that follows through from there. Next part then says, hence find the time at which the magnitude of the acceleration is a minimum. So, let's look at this magnitude. Well, it's a term that's squared, so that term is always positive no matter what happens, and the 8 squared is a positive. So the smallest we can make the magnitude is to make 12t squared minus 12 equal to 0. So the minimum occurs is at 12t squared minus 12 equals 0. And that will make the minimum magnitude at that point, at that time, 64. And so, if we solve this equation, that tells us that t squared is equal to 1, and so t will equal 1. Okay. We won't be interested in the negative solution at that point for t, because the time that we started the motion was from t equals 0. Again, for realising that the 12t squared minus 12 has to equal 0, you get 1 mark for that, and then for identifying the value of t at that moment, will give you an accuracy mark, an answer mark. So, we know then that when t equals 1 rather, that gives you the minimum magnitude of the force, which gives you an answer as we said, of 0 squared plus 8 squared rooted, which makes the magnitude of the force 8. Sorry, the magnitude of the acceleration 8, my apologies. Yeah, so we know the acceleration is equal to 8 meters per second squared. So then, to find the magnitude of the single force that would create that acceleration, we can use mass times acceleration. The mass is 7 kilograms, the acceleration we know is 8, and so the magnitude of the force will be 56 newtons. Mind you, I have assumed there that the whole thing was being measured in meters and seconds and kilograms. Yeah, so that's fine. Yeah, it does say F newtons, doesn't it? Okay, just 2 marks for that part. For realising then that it's mass times acceleration, using the correct formula would be 1 mark, and for substituting in and working out the correct value for the force will give you your 2nd mark. Hopefully that solution was helpful. For more assistance with your maths revision, please go to the Further Maths Support Programme website.